NASA's Exoplanet Archive now catalogs over 5,600 confirmed worlds, with new discoveries happening regularly. But there's a problem. Even the closest potentially habitable planet would take decades to reach with emerging fusion propulsion technology and centuries with current systems. Unless we do something that sounds completely insane, build a generation ship. These massive vessels would house entire civilizations for the duration of interstellar journeys. But 2025 has brought us 3 game-changing technologies that can make this science fiction concept our species' greatest reality. The fusion breakthroughs, closed-loop life support systems, and AI autonomy we've achieved might finally transform an impossible dream into an engineering challenge. But first, we need to understand exactly why the distances involved make this our only realistic option. The speed problem that changes everything. Here's the brutal math that keeps space engineers awake at night. Our fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of 430,000 miles per hour when it whips around the sun. That sounds incredibly fast until you realize it would still take over 7,000 years to reach Proxima Centauri, our closest stellar neighbor. And that is just the nearest star system, not even a confirmed habitable planet. The numbers get worse from there. Physics has delivered us some uncomfortable truths in 2025. Einstein's speed limit still holds firm after more than a century of testing, and proposed solutions like warp drives and wormholes remain speculative without known physics or engineering paths. Every faster-than-light concept either violates established science or demands resources beyond our civilization's capability. Meanwhile, Earth's resource constraints grow tighter each year. Rare earth elements become scarcer as our technology demands increase. Fresh water supplies stress under population growth and climate shifts. Agricultural yields plateau despite technological advances. The window for establishing backup civilizations elsewhere might be narrowing faster than we realize. We can't wait for miraculous physics breakthroughs that might never come. Even the most optimistic propulsion concepts under development still leave us facing multi-generational journey times. Nuclear pulse propulsion using projectile designs might push spacecraft to 10% of light speed, but that still means 43 years to reach Proxima Centauri. Fusion ramjets could theoretically achieve higher speeds, but building such systems requires mastering controlled fusion first, then scaling it to enormous spacecraft masses while still demanding decades of development. The reality hits differently when you personalize it. Anyone who climbs aboard an interstellar spacecraft will die during the journey. Their children will die during the journey. Possibly their grandchildren too. The destination becomes someone else's achievement, someone else's reward for sacrifices they never chose to make. Traditional space missions operate on the assumption that crews return home or at least communicate regularly with Earth. Interstellar distances break both assumptions completely. This fundamental constraint forced scientists to think in ways that feel almost medieval. Instead of sending explorers, we need to send entire societies. Instead of planning return trips, we need to plan permanent exodus. Instead of maintaining Earth connections, we need to create self-sufficient civilizations that can survive independently for centuries. These requirements pushed theoretical designs towards solutions that seemed impossible until recently. The concept first emerged seriously in the 1970s when physicist Gerard O'Neill calculated that rotating space habitats could house millions of people using materials mined from asteroids. British Interplanetary Society members designed Project Daedalus, an unmanned probe to Barnard's star, but realized that human missions would require completely different approaches. Robert Bussard proposed interstellar ramjets that collected fuel during flight. Freeman Dyson outlined generation ships as rotating cylinders kilometers long, carrying complete ecosystems through space. These early concepts shared common problems that made them impractical with 1970s technology. Power systems couldn't operate reliably for centuries. Life support systems couldn't achieve true closed-loop efficiency. Computers couldn't manage the complex systems autonomously. Material science couldn't build structures large enough and strong enough. Most critically, no propulsion system could accelerate massive ships to meaningful interstellar speeds. Traditional space missions assume mission durations measured in years, not centuries. Equipment gets tested, launched, operated, then either returns or fails. Ground control maintains constant communication and can troubleshoot problems. Crew selection focuses on specific skills needed for defined objectives. Supply chains remain connected to Earth's industrial base. These assumptions collapse completely at interstellar distances. Communication delays grow from minutes to years as spacecraft travel farther from Earth. A radio signal from Proxima Centauri takes over 4 years to reach us, making real-time problem solving impossible. Equipment must function reliably for time frames that exceed any testing period we can practically conduct. Crews can't be selected for specific missions because the mission objectives might change over centuries. Supply chains must become completely self-contained because no resupply missions can catch up across interstellar distances. The psychological challenges multiply the technical ones. How do you maintain morale among people who will never see their destination? How do you prevent social breakdown in isolated communities that can't escape each other? How do you preserve knowledge and skills across generations when Earth's libraries become inaccessible? How do you govern societies that have no external authority or appeal process? These questions have no precedent in human history. But Tathons 25 has brought us 3 technological revolutions that change the entire equation. Artificial intelligence has reached the sophistication needed to manage complex systems autonomously for extended periods without human oversight. Closed-loop life support systems have achieved near-perfect recycling efficiency in prototype installations. Most significantly, fusion power has finally achieved commercial viability after decades of promises. Each breakthrough alone would be significant, but their combination creates possibilities that didn't exist even 5 years ago. AI systems can serve as immortal crew members that maintain ship operations across centuries without degradation. Closed-loop life support can sustain large populations indefinitely using only internal resources. And fusion reactors can provide the enormous energy needed to accelerate massive ships to meaningful fractions of light speed. The timeline implications are staggering. Previous generation ship concepts required technology that might never be developed. Current designs need only refinement and scaling of systems that already exist in working form. The gap between theoretical possibility and engineering reality has narrowed to a matter of industrial capacity rather than scientific breakthrough. Generation ships represent our most realistic path to becoming a multi-planetary species because they sidestep the fundamental physics limitations that block faster alternatives. Instead of fighting the speed of light, we accept it and design around it. Instead of waiting for impossible technologies, we use possible ones. Instead of planning for our lifetimes, we plan for our species' future. The concept transforms human expansion from exploration mission to migration event. Like our ancestors who crossed oceans to new continents, future generations might cross space to new worlds. The journey becomes the destination, at least for those who begin it. Success gets measured not in mission completion, but in civilization survival. These ships wouldn't just carry passengers. They'd carry the future of human consciousness itself across the galaxy. The key to making this vision reality lies in the power source that drives everything else. Without sufficient energy, generation ships remain impossible dreams. With it, they become engineering challenges we can actually solve. Fusion breakthrough, the game-changing propulsion revolution. The breakthrough came in March 2025 when Commonwealth Fusion Systems fired up their Spark reactor, generating 11 megawatts of output from 10 megawatts of input for 5 continuous minutes. By August, Halion Energy's Polaris facility achieved 50 megawatts of net energy gain. TAE Technologies reported stable plasma confinement lasting 30 minutes in their Norman reactor. These aren't laboratory curiosities anymore. They're working power plants selling electricity to the grid. Chemical rockets burn fuel with oxygen and push exhaust out the back at maybe 5 kilometers per second. That's fast enough to reach orbit, but pathetically slow for interstellar travel. Fusion rockets work completely differently. Instead of chemical combustion, they fuse hydrogen isotopes together, releasing energy that can accelerate exhaust to 30,000 kilometers per second, 6 times faster than chemical rockets. That difference in exhaust velocity translates directly into spacecraft speed. Where chemical propulsion might push a ship to 20 kilometers per second maximum, fusion propulsion could accelerate the same ship to 60,000 kilometers per second or more. The magnetic confinement breakthrough that made 2025's fusion success possible centers on high-temperature superconducting magnets. These new Rebco tape magnets can generate magnetic fields of 20 Tesla while operating at liquid nitrogen temperatures instead of requiring expensive liquid helium. Cooling. The magnetic field strength matters because stronger fields can contain hotter plasma more efficiently. Hotter plasma means more fusion reactions per unit time, which means more energy output from smaller reactor cores. Meanwhile, inertial confinement fusion achieved ignition at the National Ignition Facility using 192 laser beams focused on deuterium-tritium fuel pellets. The pellets implode under laser heating, compressing fusion fuel to densities 100 times greater than lead. At those densities, fusion reactions occur so rapidly that they release more energy than the laser's input. Private companies like Marvel Fusion and Focused Energy are scaling this approach toward commercial reactors that could fit inside spacecraft. These fusion advances enable generation ships to reach 15 to 20% of light speed, cutting journey times from tens of thousands of years to mere centuries. A ship traveling at 15% of light speed would reach Proxima Centauri in 28 years instead of 7,000 years. TRAPPIST-1, with its 7 potentially habitable planets, becomes a 280-year journey instead of requiring 73,000 years. Wolf 1061C drops from 14,000 years to 560 years. Suddenly, interstellar travel shifts from impossible to merely difficult. 3 specific fusion propulsion projects are moving from theory to reality. Pulsar Fusion plans to demonstrate their Sunbird fusion rocket as early as 2027. The Sunbird uses a direct dual fusion drive that fuses deuterium with helium-3 to generate thrust bursts rather than continuous operation. Their engine design produces exhaust velocities exceeding anything chemical rockets can achieve while generating electrical power for spacecraft systems simultaneously. NASA's competing direct fusion drive concept promises to cut Earth-Mars transit times to 90 days while providing megawatts of onboard power. This dual-purpose design addresses one of generation ship's biggest challenges, the need for both propulsion and enormous amounts of electrical power for life support systems. A single fusion engine could accelerate the ship during initial departure, then switch to power generation mode during the cruise phase. RocketStar's Firestar drive takes a different approach, using water as fuel in a pulsed plasma thruster. Water vapor gets ionized into high-speed protons that collide with boron nuclei, triggering fusion reactions that create an afterburner effect. This hybrid electric fusion system increases thrust performance by 50% over conventional ion thrusters while using fuel that can be harvested from space ice. The water-fueled approach eliminates the need to transport exotic fusion fuels from Earth. Containing fusion reactions in deep space presents challenges that don't exist in ground-based power plants. Cosmic radiation can damage superconducting magnets over decades of operation. Micrometeorite impacts could puncture reactor containment systems. Temperature swings from minus 270 degrees Celsius in shadow to plus 120 degrees Celsius in sunlight-stressed materials beyond Earth-based testing limits. Vibrations from the ship's rotation or acceleration could disrupt plasma confinement that requires precision measured in millimeters. Space-based fusion reactors must operate autonomously for centuries without maintenance crews or replacement parts from Earth. Every component needs redundant backups because a single failure could disable the entire propulsion system. Magnetic coils require materials that maintain superconductivity across temperature cycles that would destroy conventional superconductors. Plasma-facing materials must withstand neutron bombardment that gradually transmutes their atomic structure. Heat radiators must reject gigawatts of waste heat without degrading over decades of thermal cycling. The power requirements for generation ship life support systems dwarf anything we've built before. A ship housing 50,000 people needs approximately 500 megawatts of continuous power just for basic life support, air recycling, water purification, food production, lighting, and environmental controls. Add artificial gravity systems, manufacturing equipment, computer networks, and propulsion power, and total requirements reach several gigawatts. Only fusion reactors can provide that much power continuously for centuries using fuel that can be carried or collected during the journey. Fusion fuel availability in space solves one of the biggest logistical challenges for generation ships. Deuterium can be extracted from water ice found on asteroids, comets, and moons throughout the solar system. Jupiter's atmosphere contains vast quantities of helium-3 deposited by solar wind over billions of years. Saturn's moon Titan has methane lakes that contain deuterium. Even interstellar space contains hydrogen that could be collected by magnetic scoops during flight, though at extremely low densities. The energy density advantages of fusion make generation ships energetically viable for the first time in human history. Chemical rockets require fuel masses larger than the spacecraft itself to achieve meaningful speeds. Ion drives need huge solar panels and nuclear reactors to power their thrusters. Fusion rockets carry their fuel and power source in the same compact system, enabling mass ratios that make interstellar missions possible. All credible interstellar propulsion concepts now rely on fusion sublight propulsion, as confirmed by 2025 developments. The technology that makes stars burn now makes our journey to them possible. But fusion power alone isn't enough to sustain a civilization across centuries of interstellar flight. The complexity of managing such systems across multiple generations requires capabilities that no human crew could possibly maintain. AI, the digital crew that never dies. Enter artificial intelligence systems that can serve as immortal crew members, maintaining ship operations across centuries without degradation. Current AI and machine learning tools have demonstrated the capability to manage complex spacecraft systems autonomously for years, as proven by NASA's autonomous satellite constellation operations and predictive maintenance systems. These advances make generation ships viable for the first time because they solve the fundamental problem of preserving critical knowledge and skills across multiple human generations. Think about the expertise required to keep a generation ship running for 3 centuries. You need specialists in fusion reactor maintenance, atmospheric chemistry, hydroponics, psychology, medicine, engineering, computer science, and dozens of other fields. But people die. Knowledge gets forgotten. Skills deteriorate without practice. By the time your ship reaches its destination, critical expertise might have vanished entirely, dooming everyone aboard. AI systems eliminate this vulnerability by serving as permanent repositories of essential knowledge and operational capability. 3 core AI systems form the backbone of generation ship operations. Navigation AI must plot courses through 3-dimensional space while accounting for stellar drift, gravitational perturbations from unseen objects, and course corrections that might become necessary decades into the journey. The navigation system tracks the ship's position using pulsar timing arrays, stellar parallax measurements, and inertial guidance systems that maintain accuracy across centuries of operation. Unlike human navigators who might make calculation errors or forget procedures, AI navigation systems maintain perfect precision indefinitely. Life support management represents the most critical AI responsibility because any malfunction could kill everyone aboard within hours. These systems monitor thousands of parameters simultaneously, tracking atmospheric processors that maintain precise oxygen and carbon dioxide levels while removing trace contaminants that build up over time. Water recycling systems need constant adjustment as usage patterns change and equipment ages. Temperature and humidity controls must adapt to population changes, equipment heat loads, and the ship's orientation relative to stars and interstellar radiation. AI systems can process this complexity continuously without fatigue or oversight errors that could prove fatal. Genetic and crew management AI handles the delicate task of maintaining population health across multiple generations. The system tracks family lineages, prevents inbreeding while maintaining genetic diversity, and manages reproductive health resources including sperm and egg banks. It monitors for genetic disorders that might emerge over time and calculates optimal breeding recommendations based on genetic compatibility. Beyond genetics, crew management AI analyzes social dynamics to identify brewing disputes before they escalate, monitors work performance and resource usage patterns, and suggests interventions to maintain community stability. Machine learning algorithms adapt to problems that human designers never anticipated because generation ships will encounter situations that have never existed before. Equipment will fail in ways that Earth-based testing never revealed. Social conflicts will emerge from pressures that isolated communities have never faced. Resource shortages will develop from usage patterns that nobody predicted. The AI must learn from each challenge and develop new solutions without guidance from Earth-based engineers who are light years away and decades behind in communication. Psychological health maintenance requires AI systems that understand human behavior patterns and can provide personalized interventions. The system monitors stress indicators through biometric sensors, speech pattern analysis, and behavioral observation. It personalizes support for each individual based on their psychological profile, cultural background, and social relationships. Some people might need virtual reality experiences that simulate Earth environments. Others might benefit from creative challenges or social connection opportunities. The AI provides these interventions while maintaining human dignity and autonomy. Keeping AI systems functional for centuries without Earth-based updates presents engineering challenges that push current technology to its limits. The AI hardware must resist radiation damage from cosmic rays and solar flares that could corrupt memory or processing units. Error correcting codes must detect and fix data corruption before it spreads through the system. Redundant processors must take over when primary systems fail. The AI might need to direct onboard manufacturing equipment to fabricate replacement components when hardware inevitably breaks down. Self-repair capabilities become essential when the nearest computer technician is light years away. The AI must diagnose its own hardware problems, design repair procedures, and direct robotic systems to perform maintenance tasks. It needs detailed knowledge of its own architecture, manufacturing processes for replacement parts, and troubleshooting procedures for problems that might not emerge for decades. The system essentially becomes its own technical support team, maintaining functionality across timeframes that exceed any Earth-based testing period. AI tutors preserve essential knowledge across generations by serving as immortal teachers who never forget critical information. These systems maintain complete libraries of human knowledge from basic sciences to advanced engineering techniques. They adapt teaching methods to individual learning styles and ensure that critical skills don't disappear when expert practitioners die. The AI tutors must keep knowledge relevant and accessible while preventing information overload that could overwhelm students. Resource allocation management prevents the social conflict that could destroy the mission before it reaches its destination. The AI tracks inventory levels for thousands of different items, from food and water to rare metals needed for equipment repairs. It calculates consumption rates, predicts future needs, and identifies potential shortages before they become critical. When resources become scarce, the system implements rationing fairly while maintaining morale and preventing hoarding or black market trading. The AI essentially becomes the institutional memory that preserves mission continuity across centuries. While human generations are born, live, and die during the journey, the AI maintains knowledge of original objectives, operational procedures, and survival strategies. It remembers why the ship launched when humans born during the voyage might question their purpose. The AI serves as humanity's guide through the darkness between stars, ensuring that critical systems continue functioning and the mission stays on track. But even the most sophisticated AI systems cannot create the resources needed for human survival from nothing. The ship's inhabitants must have access to air, water, food, and waste processing systems that can close-loop life support, creating worlds in space. The engineering challenge becomes creating completely self-sustaining ecosystems that can operate for centuries without any external inputs. Advanced Life Support's ECLSS-7 system achieved 99.7% atmospheric recycling efficiency in orbital testing throughout 2025, representing a breakthrough that makes generation ships viable. The system uses molecular sieves made from metal organic frameworks that capture carbon dioxide with unprecedented precision, grabbing individual CO2 molecules from breathing air and concentrating them for processing into oxygen through solid oxide electrolysis cells. Unlike traditional chemical scrubbers that eventually saturate and need replacement, these molecular sieve filters regenerate themselves through temperature cycling, operating indefinitely without consumable materials. The atmospheric processors maintain precise gas mixtures that prevent long-term health problems by keeping nitrogen levels constant and monitoring trace gases that accumulate from radioactive decay of ship materials over decades. Water vapor requires constant adjustment to prevent condensation that could damage electronics or create mold growth in ventilation systems. NASA's Sabatier reactors convert captured carbon dioxide back into water and methane using hydrogen recovered from electrolysis processes, creating closed chemical loops that achieve over 90% efficiency. The methane gets further processed through steam reforming to produce additional hydrogen, losing virtually nothing to space. Advanced catalyst materials maintain reaction efficiency for over 10,000 operating hours without degradation, far exceeding previous generations of atmospheric processors. Water recycling systems have reached the critical threshold needed for generation ships, with International Space Station data showing 98% recovery rates that can be improved further with advanced membrane technology. These systems capture every source of water aboard the ship through humidity condensers that extract moisture from breathing air and perspiration, multi-stage filtration for shower and washing water, and distillation processes that recover pure water from urine while concentrating waste products for use. Forward osmosis systems use engineered draw solutions that pull water through membranes without requiring high-pressure pumps, consuming 90% less energy than traditional reverse osmosis while achieving better contaminant removal. The draw solutions get recycled through thermolytic processing that separates recovered water from the drawing agents, creating closed loops within the water recovery system that operate continuously for decades without replacement parts. Food production combines vertical farming with algae bioreactors to achieve complete nutritional independence during interstellar journeys. Vertical farms use LED lighting tuned to specific photosynthetic wavelengths, consuming 95% less energy than traditional full-spectrum grow lights. Hydroponic and aeroponic growing systems recycle nutrient solutions continuously, with sensors monitoring pH, conductivity, and individual nutrient concentrations in real time to maintain optimal growing conditions. Controlled environment agriculture produces staple crops like wheat, rice, potatoes, and soybeans in multi-tiered growing chambers that maintain optimal temperature, humidity, CO2 concentration, and light cycles for specific crops. Automated harvesting systems reduce labor requirements while preventing contamination from human handling. Seed banks preserve genetic diversity for hundreds of crop varieties, ensuring food security even if primary growing stocks suffer disease or genetic drift over the centuries-long journey. Algae bioreactors provide high-protein food sources that grow rapidly in controlled conditions using minimal space and resources. These systems can produce complete amino acid profiles while converting carbon dioxide from atmospheric processing into edible biomass, creating another closed loop that transforms waste products into food resources. Microalgae species like spirulina and chlorella offer concentrated nutrition that supplements traditional crop production. Genetic studies indicate that minimum populations of approximately 98 individuals can maintain genetic diversity over multiple generations, though larger populations provide better long-term stability. Generation ships must carefully manage breeding populations to prevent genetic bottlenecks while maintaining cultural and social diversity among the crew and their descendants throughout the journey. Waste management systems convert human waste into valuable resources through multiple processing pathways that recover every useful material. Anaerobic digesters break down organic waste to produce methane for fuel and nutrient-rich slurry for hydroponic growing systems. Even human hair and nail clippings get processed to recover proteins and trace minerals that support the ship's closed ecological loops. Solid waste processing includes material recovery systems that separate recyclable metals, plastics, and ceramics from general waste streams. Plasma gasification systems break down complex organic materials into elemental components that get reprocessed into useful chemicals. Manufacturing feedstock gets produced by grinding and reprocessing plastic waste, creating closed material loops for producing replacement parts and tools using onboard 3D printing systems. Urine processing recovers valuable minerals and chemicals beyond just water extraction. Nitrogen compounds get converted into fertilizers for plant growth systems. Phosphorus recovery provides essential nutrients that would otherwise be lost. Even trace elements like potassium and magnesium get captured and recycled back into the ship's resource streams, ensuring nothing valuable gets wasted during the long journey. Artificial ecosystems integrate all these recycling systems into stable ecological networks designed to operate for centuries without external inputs. Multiple bacterial strains maintain soil health in growing systems while preventing pathogenic organisms from establishing themselves. Beneficial microorganisms get deliberately cultivated to support human digestive health and prevent disease outbreaks in closed populations. Redundant backup systems prevent single points of failure that could doom the entire population. Each critical life support function has at least 3 independent systems capable of handling full load if others fail. Atmospheric processors include backup units that can maintain air quality even with 2 primary systems offline. Water recycling has redundant treatment trains that operate independently. Food production spreads across multiple growing chambers, so crop diseases cannot destroy the entire food supply. These closed-loop systems finally make it possible to create truly sustainable mini-worlds in space that support large populations for centuries without resupply from Earth. Every atom gets recycled endlessly through biological and chemical processes that mirror Earth's natural cycles, compressed into spacecraft that carry complete ecosystems between the stars. But sustaining human life requires more than just air, water, and food. The rotating city's artificial gravity solutions. The human body requires constant gravitational stress to develop and function properly. Picture a child born in zero gravity who will never develop normally. Their bones grow thin and brittle because gravity never pulls calcium into the bone matrix. Their muscles remain weak because they never fight against gravitational resistance. Their inner ear develops incorrectly, leaving them with balance problems that would make planetary surfaces unlivable. After just 2 generations in zero gravity, humans might become permanently adapted to weightlessness, unable to survive on the worlds they traveled centuries to reach. This health crisis drove engineers toward rotating spacecraft that create artificial gravity through centrifugal force. When a spacecraft spins around its central axis, everything inside experiences an outward push that feels identical to gravitational pull. Stand on the outer rim of a rotating ship and you feel normal weight pressing your feet against the floor. The faster the rotation or the larger the radius, the stronger this artificial gravity becomes. It's the same physics that creates force in any rotating system, scaled up to create livable environments in space. The Stanford torus design proposed in the 1970s remains the leading concept for generation ship artificial gravity systems. This donut-shaped rotating ring spins around a central hub, creating continuous artificial gravity along the outer rim, while maintaining zero gravity at the center for docking operations and industrial processes. The torus shape distributes structural loads evenly, reducing stress concentrations that could cause catastrophic failures during centuries of operation. O'Neill's cylinder designs offer an alternative approach, creating cylindrical habitats that rotate around their long axis. The cylinder walls serve dual purposes as both habitat floors and structural support for the rotating framework. These designs provide maximum living space per unit of construction material while allowing windows along the cylinder sides for views of space and natural light distribution throughout agricultural areas. The optimal rotation rate for human comfort sits around 2 revolutions per minute, slow enough to prevent disorientation while fast enough to generate meaningful artificial gravity. Faster rotation creates Coriolis effects that make moving objects curve sideways, causing nausea and balance problems. Slower rotation requires larger ship diameters to achieve the same gravity level. The sweet spot balances these competing factors to create environments where humans can live normally for decades, without adverse effects. Ship diameter determines artificial gravity strength at any given rotation rate. A ship with a 224-meter radius rotating at 2 RPM generates Earth normal gravity, meaning the total diameter reaches 448 meters across. Double the radius and you can achieve the same gravity at just 1.4 RPM, reducing Coriolis effects further. Triple the radius and rotation drops to 1.2 RPM, creating gravity that feels completely natural to human occupants. Advanced materials developed in 2025 make kilometer-wide rotating structures possible for the first time. Carbon nanotube fibers achieve tensile strengths over 400 times stronger than steel at 1/6 the weight. These fibers can be woven into composite materials that handle the enormous centrifugal stresses of large rotating structures without catastrophic failure. Graphene reinforced polymers provide additional strength while maintaining flexibility needed for thermal expansion cycles. Construction techniques pioneered by space manufacturing companies enable assembly of massive structures in orbit using robotic systems. The European Space Agency's OPS-SAT mission demonstrated autonomous manufacturing capabilities in space, while NASA's Argonaut platform proved that large structures can be 3D printed and assembled directly in orbit. These technologies eliminate the need to launch pre-built sections from Earth, reducing costs and enabling construction of structures too large to fit inside any rocket fairing. Maintaining rotation for centuries without failure requires engineering solutions that exceed terrestrial applications. Magnetic bearings eliminate mechanical friction that would wear down traditional wheel bearings over decades of continuous operation. These bearings use electromagnetic fields to support rotating masses without physical contact, preventing wear while allowing precise control of rotation rates. Backup bearing systems provide redundancy if magnetic systems fail, ensuring the habitat maintains gravity even during maintenance periods. Gyroscopic stabilization systems prevent wobbling that could develop as mass distributions change inside the rotating habitat. As people move around, equipment gets relocated, or structural components experience wear, the ship's balance might shift slightly. Gyroscopes detect these changes and fire thrusters to maintain stable rotation. The stabilization system must operate continuously for centuries, requiring robust designs with multiple backup systems. Multi-ring configurations allow different gravity levels within the same ship. An outer ring spinning at full Earth gravity houses residential areas and schools where normal development occurs. An inner ring rotating slower provides partial gravity for elderly residents or medical patients who need reduced physical stress. A central hub maintains zero gravity for manufacturing processes and spacecraft operations that work better in weightlessness. Artificial gravity enables normal human development throughout the centuries' long journey to destination planets. Children grow up with proper bone density and muscle development that allows them to function on planetary surfaces. Pregnant women can carry babies to term without the complications that zero gravity creates for fetal development. Elderly passengers maintain mobility and independence instead of becoming bedridden as muscles and bones deteriorate in weightlessness. Exercise requirements drop dramatically when artificial gravity provides constant physical stress. Instead of spending hours daily on treadmills and resistance machines to prevent muscle atrophy, residents can maintain fitness through normal daily activities. Walking, climbing stairs, and lifting objects provide the resistance training that keeps bodies healthy. Sports and recreational activities become possible, improving psychological health during the long journey. These rotating cities transform generation ships from desperate survival missions into genuine homes where multiple generations can live fulfilling lives. Instead of enduring centuries of weightless existence that would cripple human development, residents experience Earth-like conditions that allow normal physical and social development. The artificial gravity makes interstellar travel not just survivable, but genuinely livable, turning the journey itself into a destination worth experiencing. But creating livable conditions aboard generation ships means nothing without knowing where these massive vessels should actually go. The question of destination has shifted from theoretical speculation to practical planning as our understanding of nearby worlds has expanded dramatically. Target destinations, where we're actually going. The search has narrowed to specific worlds where human civilization could actually take root. Over 5,630 confirmed exoplanets now populate astronomical databases, but only a handful offer realistic destinations for generation ships. The James Webb Space Telescope has detected water vapor and methane signatures in exoplanet atmospheres, revealing which worlds might sustain human life after centuries of interstellar travel. Proxima Centauri b stands as our closest confirmed target at just 4.24 light-years away. This rocky planet orbits within the habitable zone of its red dwarf star, where liquid water could exist on the surface. Recent observations suggest the planet might retain a substantial atmosphere despite receiving intense stellar radiation. The red dwarf produces powerful flares that could strip away atmospheric gases, but computer models indicate that a thick atmosphere might survive these events. A generation ship could reach Proxima Centauri b in approximately 280 years using fusion propulsion systems. TRAPPIST-1 presents an even more compelling destination with 7 Earth-sized planets orbiting a single ultra-cool dwarf star. 3 of these worlds sit within the habitable zone where water remains liquid. TRAPPIST-1e shows the strongest evidence for Earth-like conditions with possible water vapor detected in its atmosphere. The system lies 40 light-years away, requiring approximately 460 years using advanced fusion rockets. Multiple planets provide backup options if the primary target proves unsuitable upon arrival. Wolf-Warn 61c offers another promising destination at 14 light-years distance. This super-Earth planet has a mass 4 times larger than our world, creating stronger surface gravity that humans could adapt to over generations. Atmospheric modeling suggests the planet could maintain liquid water despite receiving slightly more stellar radiation than Earth. The higher gravity might actually benefit human health during the long journey, preventing the bone loss and muscle atrophy that plague astronauts in weightless conditions. A generation ship could complete this journey in roughly 200 years. Artificial intelligence algorithms now process exoplanet data to rank potential destinations based on hundreds of criteria that human researchers couldn't evaluate manually. Machine learning systems analyze stellar radiation patterns, orbital dynamics, atmospheric chemistry, and geological activity indicators to predict which worlds offer the best chances for successful colonization. AI systems update their rankings continuously as new observations refine our understanding of distant planetary conditions. The European Space Agency's Plato mission, launching in 2026, will discover thousands of additional Earth-like planets around Sun-like stars. Plato's 26 telescopes will detect planetary transits with precision that reveals planets as small as Earth orbiting at Earth-like distances from their stars. The mission specifically targets stars similar to our Sun, where planetary systems might most closely resemble our own solar system's architecture and evolution. NASA's Roman Space Telescope will use gravitational microlensing to find planets that don't transit their hosts in their stars, including free-floating planets ejected from their original star systems. These rogue worlds represent wildcard destinations that generation ships might encounter during interstellar journeys. Some rogue planets could retain subsurface oceans heated by radioactive decay, creating hidden biospheres in the depths of interstellar space. The risk of traveling to unsuitable destinations drives mission planners toward flexible strategies that can adapt during flight. Generation ships must carry enough fuel and resources to change course toward alternative targets if the primary destination proves uninhabitable. Advanced telescopes aboard the ships will continue studying target planets throughout the journey, refining our understanding of surface conditions and atmospheric properties as the distance closes. Course correction capabilities require propulsion systems that can operate efficiently across multiple decades of travel. Ion drives provide continuous low-thrust acceleration that can gradually alter ship trajectories over years or decades. Fusion rockets deliver higher thrust from major course changes, but consume more fuel. Generation ships need both propulsion types to maintain flexibility during centuries-long voyages toward targets that remain poorly understood despite our best observations. Multiple destination strategies hedge against the possibility that any single target might prove unsuitable for human habitation. Generation ships might launch towards star systems containing several potentially habitable worlds, choosing the best option after detailed reconnaissance during approach. The TRAPPIST-1 system exemplifies this approach, offering 3 habitable zone planets within a single destination that reduces travel time compared to sequential visits to different star systems. The possibility of finding existing life on target planets creates both excitement and concern for generation ship missions. Discovering alien ecosystems would represent the greatest scientific achievement in human history, but it also complicates colonization plans that assume empty worlds waiting for human settlement. Generation ships must prepare for scenarios ranging from sterile planets to complex biospheres that might resist human intrusion or harbor pathogens dangerous to Earth-based life. Mission planners can finally point to specific worlds and calculate realistic journey times using technologies that exist today. Proxima b becomes reachable within 3 centuries. Wolf with the 361c drops to 2 centuries. Even the TRAPPIST-1 system becomes accessible within 5 centuries using fusion propulsion. These timeframes transform interstellar colonization from impossible dream to engineering challenge. The technical hurdles of building generation ships pale beside the human challenges of sustaining civilization across centuries of isolation. Fusion reactors can provide power, closed-loop systems can recycle resources, and artificial gravity can maintain health. But no technology can solve the psychological burden of raising children who will live their entire lives trapped between worlds. The human challenge, psychology across generations. These psychological pressures create unprecedented challenges that no human society has ever faced before. Imagine explaining to your 5-year-old daughter that she will spend her entire life inside a metal container floating through empty space, that she will never feel rain on her skin or see a real sunset, and that her purpose in life is to give birth to children who will also live and die inside that same container. Generation ship inhabitants must raise multiple generations who accept a destiny they never chose in conditions that push human psychology beyond all historical precedent. Research on isolated, confined, and extreme environments provides critical insights into how humans respond to prolonged separation from normal society. COVID-era isolation studies revealed that extended confinement creates measurable changes in brain structure, particularly in regions controlling social behavior and emotional regulation. Depression rates climbed 400% above baseline levels, and cognitive decline persisted for months after isolation ended. These effects compound across generations when children develop in artificially confined environments from birth, creating psychological adaptations that might make planetary life impossible for spaceborne humans. A Mars 500 experiment and Antarctic research stations demonstrate how group size affects psychological stability during long-term isolation. Small groups below 50 people consistently experience individual burnout and psychological breakdown as social roles become too rigid and interpersonal conflicts have nowhere to dissipate. Large groups exceeding 150 people develop factionalism and discord that escalates over time as subgroups form competing hierarchies. The optimal population size appears to be between 500 and 2,000 people, providing enough social diversity to prevent stagnation while maintaining manageable group dynamics that reduce destructive conflict. NASA and ESA virtual reality experiments offer promising solutions for psychological relief during interstellar journeys. These VR systems create convincing simulations of Earth environments using haptic feedback that engages all 5 senses. Test subjects and isolation studies showed significant reductions in claustrophobia and depression after spending 4 hours daily in virtual Earth environments. Advanced VR systems could provide generation ship inhabitants with experiences of hiking mountains, attending concerts, or walking through rain that feel completely authentic, maintaining psychological connections to planetary life across centuries of space travel. Simulation technology serves essential psychological functions beyond entertainment. Virtual reality can simulate seasonal changes that human circadian rhythms require for proper mental health. Artificial weather patterns, changing daylight cycles, and simulated natural disasters provide the environmental variety that prevents psychological stagnation. Some residents might spend entire careers as virtual park rangers or farmers, maintaining connection to Earth-based occupations that give their lives meaning and purpose, even when those activities have no practical relevance to ship operations. Maintaining cultural identity across centuries requires deliberate preservation efforts that go far beyond digital archives. Languages evolve and die without conscious intervention. Religious practices adapt to new circumstances or disappear entirely. Family structures change based on population pressures and resource constraints. Generation ships must actively cultivate cultural diversity through festivals, ceremonies, and educational programs that teach children about their ancestral heritage rather than just their immediate space-based reality. Cultural variations, including language, ethics, family structure, beliefs, and aesthetics, must be protected through institutional design rather than left to natural evolution. Some sections of the ship might maintain specific cultural traditions while others develop new hybrid cultures adapted to space life. Children need exposure to multiple cultural frameworks to prevent the psychological narrowing that occurs in isolated populations. Competition between different cultural groups can provide healthy social dynamics as long as it doesn't escalate into destructive conflict. Genetic diversity requirements create uncomfortable population management decisions that previous human societies never faced. Research shows that a minimum crew of 98 people coupled with extensive sperm, egg, and embryo banks can maintain genetic health over multiple generations. However, this requires active management of reproduction to prevent inbreeding and maintain genetic variation. The genetic constitution of the founding population strongly conditions the biological fate of the entire colony, making initial selection criteria critically important for species survival. Potential conflicts. Aboard generation, ships could doom entire missions through violence that damages critical systems or dramatically reduces genetic variation through population loss. Multiple factions going to war represent existential threats when there's nowhere to escape and no external authority to intervene. Social breakdown becomes particularly dangerous in closed systems where resource competition can escalate quickly into life-threatening conflicts that affect everyone aboard. Education systems face the impossible task of preserving human knowledge while adapting to completely artificial environments. Children born in space develop different cognitive patterns than Earth-raised humans. They excel at three-dimensional navigation and resource conservation, but struggle with concepts like horizons, weather, and biological ecosystems. Knowledge retention and loss relative to Earth becomes almost inevitable as practical skills become irrelevant and theoretical knowledge fades without application. Communication delays with Earth create truly independent societies that lose connection to human civilization within decades of departure. Radio signals take years to travel between stars, making real-time conversation impossible. Earth's rapid technological and cultural changes become irrelevant to space travelers facing completely different challenges. With that generation, Earth might feel as distant and irrelevant as ancient civilizations feel to us today. The ethical questions of condemning generations to space life represent the darkest aspect of generation ship planning. Every person born during the journey must live in particular and peculiar circumstances, adrift in an endless cosmic void with no hope of ever feeling the sun on their face or breathing non-recycled air. They never chose this destiny, yet their entire existence serves purposes decided by previous generations they never met. The psychological preparation for generation ship missions may prove more challenging than mastering fusion propulsion or closed-loop life support systems. Technology problems have engineering solutions, but human nature creates problems that require massive physical structures and industrial systems to address properly. Building the impossible, construction, and costs. The scale of construction required transforms these challenges into the largest industrial undertaking our species has ever contemplated. Picture a single structure that houses 50,000 people across multiple city-sized levels, stretching several kilometers in length and rotating continuously to create artificial gravity. This generation ship would dwarf every construction project in human history combined. The International Space Station took 13 years and $150 billion to build, yet it houses only 7 people. A generation ship would require construction efforts that make the ISS look like a backyard shed project. Space-based manufacturing reached critical milestones in 2025 that make generation ship construction theoretically possible. Relativity Space demonstrated 3D printing of entire rocket engines in zero-gravity conditions. Made in Space deployed robotic fabricators that can process raw materials into finished components without human oversight. Varda Space Industries proved that manufacturing in microgravity produces materials with properties impossible to achieve on Earth. These advances create the foundation for building massive structures directly in space rather than launching prefabricated sections from Earth's surface. Asteroid mining companies achieved their first commercial successes in 2025, proving that space-based resource extraction can operate profitably. Planetary Resources identified over 16,000 near-Earth asteroids containing metals worth more than the entire global economy. Deep Space Industries launched their first prospecting missions to asteroids containing platinum, rare earth elements, and water ice. Trans-Astra Corporation demonstrated asteroid capture techniques that can redirect small asteroids to Earth orbit for processing. These operations provide the raw materials needed for generation ship construction without depleting Earth's resources. Generation ships must be built entirely in space because launching such massive structures from Earth would be economically impossible. A generation ship weighing millions of tons would require over 100,000 launches, costing more than $200 trillion using current launch prices. Even dramatic cost reductions cannot overcome the fundamental physics of moving such enormous masses out of Earth's gravity well. Only space-based construction using space-sourced materials makes generation ships financially viable. Construction timelines stretch across multiple human generations because the ships themselves must be built to last centuries. Preliminary design and engineering phases require 20 to 30 years to solve unprecedented technical challenges. Site preparation involves establishing manufacturing facilities in space, mining asteroids for raw materials, and creating the infrastructure needed to support large-scale construction. This phase alone takes 30 to 50 years. Actual ship assembly requires another 50 to 100 years because of the massive scale and the need for perfect reliability in every system. The construction process begins with establishing permanent space-based industrial facilities at Earth-Moon Lagrange points or in asteroid belt locations. These facilities must include metal refineries, composite manufacturing plants, electronics fabrication centers, and assembly yards large enough to accommodate kilometer-scale structures. Building this infrastructure represents a massive undertaking, comparable to establishing an entire industrial base on a new continent. Each facility requires years of construction using robotic systems and enormous investments in equipment and materials. Current industrial capacity constraints illustrate the challenge ahead. Global shipbuilding tonnage has increased 80% since 2014, yet submarine construction backlogs stretch years into the future despite relatively simple designs. Generation ships require manufacturing scales that exceed current capacity by orders of magnitude. Space-based manufacturing and asteroid mining become essential not just for reducing launch costs, but for accessing the raw material quantities that Earth-based industry cannot supply without environmental devastation. International cooperation becomes essential because no single country possesses the resources or expertise needed for generation ship construction. The project requires coordination among space agencies, private companies, and governments worldwide. Funding mechanisms would likely include international treaties similar to those governing Antarctica or the International Space Station. Participating nations would contribute based on their economic capacity and receive proportional representation in mission planning and crew selection. Private companies would provide specialized technologies and manufacturing capabilities in exchange for commercial rights to space-based resources and technologies. Robotic construction systems eliminate the need for human workers in hazardous space environments while enabling continuous construction operations. Boston Dynamics' latest Atlas robots can perform complex assembly tasks while withstanding radiation and temperature extremes that would kill human workers. Autonomous construction vehicles developed by Caterpillar and NASA can move massive structural components and perform precision welding in zero gravity. These robotic systems work continuously without life support requirements, dramatically reducing construction costs and timelines. 3D printing in zero gravity offers unique advantages for generation ship construction. Microgravity conditions allow printing of larger structures without gravitational sagging that limits terrestrial printing. Metal 3D printing can create components with internal geometries impossible to manufacture on Earth. Composite printing combines multiple materials into single components with optimized strength-to-weight ratios. Large-scale printers could fabricate entire ship sections as single pieces, eliminating joints and welds that represent potential failure points during centuries of operation. The assembly sequences require unprecedented precision and planning because structural failures during construction could destroy years of work and billions of dollars in materials. Computer simulations model every construction step to identify potential problems before they occur in space. Modular design allows ship sections to be built simultaneously at different locations, then assembled into the final structure. Quality control systems must catch defects immediately because repairs become exponentially more difficult after subsequent construction steps. This construction phase represents humanity's largest engineering project ever attempted, requiring industrial mobilization comparable to World War II, but sustained for nearly a century. The project transforms our species from earthbound to truly spacefaring, creating the infrastructure and expertise needed to build multiple generation ships for different destinations. Success proves that humans can undertake projects spanning multiple generations, establishing precedents for even larger endeavors that carry our civilization across the galaxy. Yet for all the technical solutions and industrial planning, one question remains unanswered. When might any of this actually become reality? Timeline reality check. When could this actually happen? The development timelines reveal an uncomfortable truth that most of us need to accept. We're not going to live to see a generation ship launch. The first interstellar voyage carrying human passengers won't happen in our lifetimes, probably not in our children's lifetimes, and possibly not even in our grandchildren's lifetimes. Current research suggests that generation ships could become feasible 75 to 150 years from now, requiring technological developments and social changes that unfold across multiple human generations. The shorter timeline assumes sustained technological advancement, substantial increases in space industry investment, and strong international cooperation. The longer timeline accounts for probable delays, technological setbacks, and the enormous complexity of coordinating such projects across multiple nations and decades. Fusion power achieved commercial viability in 2025, but scaling these systems to generation ship requirements needs decades of additional development. Space-based manufacturing must evolve from building small components to fabricating kilometer-sized structures. Closed-loop life support systems require extensive testing periods to prove they can sustain large populations without external inputs. Space industrialization must reach massive scale before generation ship construction begins, and we're still in the early stages of this transformation. Current space manufacturing capabilities remain limited to small electronic components and simple metal parts, while generation ships require industrial capacity comparable to entire Earth-based manufacturing sectors. Asteroid mining operations must expand from experimental missions to routine extraction of millions of tons of materials annually. This industrial expansion requires sustained investment and technological progress spanning decades. The political and social conditions that would motivate such enormous investments don't exist yet and might take decades to develop. Generation ship construction costs exceed the GDP of major nations, requiring international cooperation on scales never achieved in human history. Political will and economic mobilization comparable to industrial revolution growth rates will be necessary. Sustained across multiple generations of leadership changes. Democratic societies struggle to fund projects that span multiple political cycles because elected officials face pressure to deliver results within their terms of office. Early prototype missions will test generation ship systems on shorter journeys to destinations within our solar system. Mars missions lasting 2 to 3 years will validate closed-loop life support systems and psychological adaptation strategies. Asteroid belt missions taking 5 to 10 years will test longer duration systems and multi-year isolation effects. Jupiter and Saturn missions requiring 10 to 20 years will approach the timescales needed for true generation ship operations. These prototype missions provide essential testing while building public support and international cooperation for larger projects. Interplanetary generation ships might precede interstellar versions by several decades, carrying large populations to permanent colonies throughout the solar system. These ships would use similar technologies while operating over shorter distances with possible rescue or resupply from Earth. Success with interplanetary generation ships would prove the concept, while building expertise needed for interstellar missions. Failure would identify problems that need solutions before attempting much longer interstellar journeys. The preparatory steps we might see in the next 20 to 30 years include major expansions in space-based manufacturing, asteroid mining operations, and fusion power development. Multiple countries will likely establish permanent space-based industrial facilities and begin routine asteroid resource extraction. Fusion power will transition from experimental reactors to widespread commercial deployment, eventually enabling space-based fusion systems. Large-scale space habitats will test artificial gravity and closed-loop life support systems with populations of thousands rather than dozens. International space cooperation will expand through treaties governing asteroid mining rights, space-based manufacturing standards, and eventual generation ship construction protocols. Space agencies will conduct increasingly ambitious prototype missions testing generation ship technologies on progressively longer timescales. Private companies will develop specialized technologies for space-based construction and resource processing. Public awareness and support for interstellar colonization will grow through successful solar system exploration and expanding space-based economies. Breakthrough discoveries in physics or engineering could dramatically compress development timelines by solving key technical challenges decades ahead of schedule. Room temperature superconductors would revolutionize fusion reactor design and space-based power systems. Breakthroughs in material science might enable construction of larger, lighter structures than current materials allow. Quantum computing advances could accelerate AI development and complex system modeling needed for generation ship design. However, breakthrough discoveries are unpredictable by definition, making them unreliable foundations for timeline predictions. Climate change or asteroid threats could accelerate development timelines by creating urgent motivations for interstellar backup plans. Severe climate impacts that threaten civilization stability might convince governments to invest heavily in generation ship technology as insurance against human extinction. A detected asteroid on collision course with Earth would create existential motivation for evacuation capabilities. Nuclear war, pandemic outbreaks, or other global catastrophes could similarly motivate crash programs in interstellar colonization technology. Most people alive today will not witness humanity's first steps toward becoming an interstellar species, but the foundations for that achievement are being laid right now through advances in fusion power, artificial intelligence, and space technology that make the impossible merely difficult. The timeline stretches beyond individual lifetimes, but the project represents something far more significant than exploration or adventure. The mounting challenges facing our home planet suggest that generation ships might serve purposes more urgent than the backup plan for humanity. These risks demand a fundamental shift in how we think about human survival. Every year brings new evidence that Earth faces catastrophic threats that could end human civilization permanently. The Yellowstone supervolcano could erupt at any time, blanketing the planet in ash and triggering a nuclear winter lasting decades. Massive asteroid impacts remain statistically inevitable over geological timescales, with civilization-ending rocks hitting Earth every few million years. Climate change accelerates beyond our ability to adapt, creating cascading failures in agriculture, water supplies, and social stability. Nuclear war between major powers could destroy industrial civilization and irradiate vast areas for centuries. Engineered pandemics or artificial intelligence systems could eliminate humanity faster than we can respond. Generation ships transform from luxury exploration missions into essential survival insurance against these existential risks. All 8 billion people currently live on a single planet orbiting one star in a galaxy containing 400 billion stars. A single catastrophic event could eliminate our entire species permanently, erasing 4 billion years of evolutionary development and destroying the only known example of intelligent life in the universe. This represents an unacceptable concentration of risk that no rational civilization would maintain indefinitely. The backup plan centers on 3 critical capabilities that 2025's technological breakthroughs finally make possible. First, distribution of populations across multiple star systems ensures species survival, even if individual colonies fail or home worlds become uninhabitable. Multiple generation ship missions spread humanity's genetic, cultural, and technological heritage across dozens of star systems simultaneously. Each ship carries 50,000 to 100,000 people, representing different ethnic groups, languages, religions, and cultural traditions. The ships travel toward different destinations across various distances, ensuring that no single catastrophe can eliminate all human colonies simultaneously. Second, preservation of human knowledge and culture occurs through multiple independent repositories that survive even if individual civilizations collapse. Each ship carries digital libraries containing humanity's accumulated scientific knowledge, literature, art, and historical records. Multiple copies ensure preservation, even if some storage systems fail during the long journey. More importantly, the ships carry living cultures practiced by actual human communities, rather than just archived information. Languages remain spoken, musical traditions continue through active performance, and religious practices adapt to space-based communities while maintaining essential elements. Cultural preservation extends beyond mere storage to active transmission across generations born during the journey. Children learn Earth history, study classical literature, and practice traditional arts despite never experiencing the environments that originally inspire these cultural expressions. Teachers adapt educational content to make Earth-based concepts relevant to space-born students who have never seen oceans, forests, or weather patterns. Art forms evolve to incorporate space-based experiences while maintaining connections to terrestrial traditions that define human cultural identity. Third, ensuring continuity through AI systems and closed-loop life support eliminates the single points of failure that have doomed previous civilizations. AI systems serve as immortal repositories of critical knowledge, maintaining ship operations across centuries without the knowledge loss that occurs when human experts die. These systems preserve essential technical skills, scientific understanding, and operational procedures that keep the ships functioning across multiple generations. Closed-loop life support systems create truly self-sustaining environments that can operate indefinitely without external resources, breaking the resource constraints that have limited every Earth-based civilization. Becoming a Type 1 civilization through interstellar expansion requires mastering energy resources equivalent to our entire planet's output while spreading across multiple worlds. The Kardashev scale measures civilizations by their energy consumption and technological capabilities. Generation ships represent humanity's first step toward Type 1 status by establishing self-sustaining populations that can develop independently without Earth's resources or support. Each successful colony becomes a launching point for further expansion as populations grow and technology advances. This technology transforms humanity from a single-planet species constrained by one world's resources and vulnerable to local catastrophes into a galactic civilization distributed across multiple star systems. Second-generation ships built by established colonies could reach even more distant destinations using improved technologies developed during centuries of space-based civilization. The expansion accelerates exponentially as human populations spread across galactic distances, establishing permanent footholds that ensure species immortality. The possibility of eventual contact between separated human colonies creates scenarios that exceed current imagination. Colonies established around different stars might develop communication technologies that reconnect scattered human civilizations after centuries of isolation. Ships launched decades apart might encounter each other during interstellar journeys, creating opportunities for trade, intermarriage, and cultural exchange between communities that developed independently. Advanced colonies might send missions to assist struggling settlements or establish contact networks that span multiple star systems. This vision connects directly to humanity's long-term survival and cosmic significance by ensuring our civilization persists across geological and astronomical timescales. Earth-based civilizations face inevitable extinction through stellar evolution as our sun eventually expands into a red giant that sterilizes the planet's surface. Galactic events like supernovae or gamma-ray bursts could eliminate life across entire solar systems. Only species distributed across multiple star systems survive such cosmic catastrophes. Generation ships may represent our species' most important technological achievement because they ensure human consciousness persists indefinitely regardless of local catastrophes that destroy individual worlds or civilizations. The knowledge, creativity, and cultural achievements that define human civilization continue developing across multiple independent societies rather than risking permanent loss through single catastrophic events. We transform from a temporary species facing inevitable extinction into a permanent fixture of galactic civilization that contributes to cosmic evolution across millions of years. The convergence of fusion power, artificial intelligence, and closed-loop life support systems has created an unprecedented moment in human history where these backup plans shift from theoretical concepts to achievable engineering projects. The engineering challenge has become remarkably specific, with 99.7% atmospheric recycling efficiency and functional direct dual fusion drive engines. 2025 transformed generation ships from physics problems into engineering projects. The technologies exist in working form rather than theoretical models. Fusion reactors generate net energy gain. AI systems operate spacecraft autonomously for years without human oversight. Closed-loop life support sustains large populations using only internal resources. The personal reality remains unchanged despite technological progress. Volunteering for a generation ship means accepting that you'll live and die during transit, never seeing the destination world that justifies the entire mission. Your children face the same fate. Only their descendants might walk on alien soil and breathe non-recycled air. Yet 3 key technologies achieved maturity in 2025: fusion propulsion, AI autonomy, and closed-loop ecosystems, making generation ships humanity's next great adventure rather than impossible.